just to make this more interesting, we could talk about conformal mappings with some of our old potentials that you've seen before. But it's more interesting to talk about ideal fluid flow problems because they're really hard and maybe you've never seen them before. So we'll take a little bit of an aside from complex variables and derive what the ideal fluid flow streamlines and complex potential is. But there's nothing really new in content in the sense that you've seen all the math and know why people would do this. So you've seen electric potentials, aka voltage, and know how they relate to the electric fields. So if I have a bunch of electric field lines, I could think about them as the direction that a positive charge would want to run downhill, as it were, so less energy. So these are the electric field lines, and these are the voltages. So you can also think about them in the sense of topography and gravitational fields, like the topo lines on a map, is that if you're following a topo line, like here, if I go up and down, I'm following one of these field lines of constant voltage or equipotentials, I'm neither gaining nor losing energy. So it's like following a contour on a map without going up or down. And the path that a particle would roll downhill, either with gravity or if it were a charged particle in an electric field, is the direction of the field line. And you may or may not have seen this proved or had it stated without proof, but these are all perpendicular. So what's true is field lines intersect with equipotentials at a 90-degree angle. And that's true about gravitational fields and their potentials as well. So if I wanted to put a satellite in orbit and at no point was it changing its gravitational potential energy, I think I would choose a circular orbit. And if I wanted it to have more gravitational energy, technically less negative gravitational energy, I would pick a bigger circular orbit and a bigger circular orbit still. So these would be gravitational potential lines. So gravitational equipotentials. We'll call them phi G, and maybe we should have called this phi E for electric. So just because of the way that the modern pedagogy works is that you talk a lot about electric fields, but they're probably never actually defined. Their definition would follow analogously from the electric fields if all you knew about was potentials. So the gravitational field lines are these things, which are locally perpendicular to the equipotentials. And you could think about them as the direction that a particle would fall if I were to release it from rest here. So that is what the gravitational field is. And likewise, every time these things intersect, they do so that the equipotentials and the gravitational fields are perpendicular. So these are all 90-degree angles. Okay, so that's the primer. And what we're going to do is extend that to a new physics problem of ideal fluid flow and talk about steady flow. And we'll talk about, as the name suggests, very ideal fluids. And you'll see for all of these examples, these two and fluids, how complex variables can be really useful. So let me consider very shallow water or water whose depth, the fluid flow doesn't change as I go down in depth, which is to say, let me just think about 2D. And imagine that there's some fluid. Fluid could be water or air or neon, so any gas or liquid. And I think about a point. So maybe you're thinking about, the air over your head on a map. And at some point, the air has a velocity v, right? And at a different point, the air has a velocity v. And at a different point, different one still. And hopefully we don't have a tornado, but that's kind of what I'm drawing here. So something like that. So there is a field in general that we can associate with fluid flow. X, Y, Z, T would be the most general way of describing it because it is in 3D. But we're not going to talk about this. So that's a tough problem. What we're going to talk about is 2D steady state flow. So 2D steady state flow means, yes, 2D, but it also means that if you look at any point in time, it's going to be identical, which is to say the velocity of your anemometer, which is a wind speed detecting device, is going to read the same thing no matter when you take the measurement. So 2D steady state means that we don't care about time. Okay. And we're going to talk about ideal or perfect fluids as well. And ideal or perfect fluids have the following properties. They are incompressible. Which means that things like this are forbidden. I cannot grab a handful of the fluid and squeeze it so that it's smaller. Imagine that the molecules are, perfectly rigid spheres and they're packed together. If you put one in, another one will pop out. So that's what incompressible means. So the question is, what does that mean mathematically? So the mathematical expression of an incompressible fluid is, think about your vector calculus from earlier in the quarter, is that this must be 0. So incompressible means that we have a vanishing divergence. Okay, this one's a little bit more implausible, but this is what an ideal fluid is, irrotational. And an irrotational fluid means that basically no hurricanes. This is forbidden. And you guessed it, this will mean that the curl of our velocity field will also be 0. That will be a vector 0. And then finally, we have a third condition, is that we're viscosity free. And you can think about that as frictionless. And that's essentially a condition that lets us talk about steady state flow, because if we did have a viscosity, what would happen is that the kinetic energy of the fluid would be leaking into thermal energy, right? So if you have friction or viscosity, you're going to heat up, and this would violate our steady state condition. So you can't have a steady state flow if the thing's got any sort of viscosity or friction. And the manifestation of that is just, yeah, we can actually talk about steady state. The way that you want to think about it in terms of how you visualize the field is that if I have two frictionless blocks, one sliding on top of another, and yeah, maybe even on a frictionless surface, this is okay. Is that neighboring velocities or speeds can be different. So frictionless means that this is an okay thing to have. I don't have any friction in between the two, means that it's okay to have a persistent situation where the velocity of the upper block is different than the lower one. So this really lets us do steady state, is the point. Okay. So if you dig back into the mathematics that we employed when we talked about, for instance, conservative vector fields and forces, what you realize is that I can use these conditions to derive some things about V, so the vector field V. So what I can say is, because we're curl-free, our irrotational condition is that there exists a potential function. In the same way that if I have a curl-free force field, then I can define a potential, like a typical potential. So for irrotational fluids, that means there exists some scalar field such that V is equal to the gradient of phi. And I could call that phi F for phi fluid, but we're going to have enough symbols, so this is phi. And I will say this is, maybe if your alarm is going off about this definition, is that the fluid people decided they don't like that minus sign. So you're probably used to seeing a minus sign when you get from a conservative force field to a conservative force field from potential. In fluid dynamics, they don't do that, just because they don't feel like it. I don't know why. So we can define a scalar function phi such that this is true. A velocity potential, if you will. And what we can also do is define something that's analogous to our gravitational field or our electric field. So in the same way that electrostatics and gravitational physics have both a potential and a field, we can define the field associated with this. So remember, V is just a discrete bunch of vectors. And this is a scalar function. So we can define a thing called phi, called the stream function. And the stream function is analogous to electric field lines, not the arrows, but the lines, connected lines you drew in 1220, or electric field lines, which probably you talked a little bit less about. So the stream function satisfies the condition that this thing, psi, is constant for the lines upon which the fluid flows. And, you know, full fine print, the lines upon which steady state fluid flows. Barely made it. Great. Okay. I will quickly show you guys some streamlines of a stream function, but I'm pretty sure you've seen them. But just to connect that with something that, you know, if you're thinking, I think I know what that is, you do. So these are essentially streamlines. So put something in a wind tunnel, and then this is, you know, it is titanium oxide smoke or something that they inject in these nozzles, and then it flows over. So if you were a molecule of whatever this gas is, you know, air, nitrogen, you would follow a streamline. Okay, and this sort of looks like what we're going to do, except we will not have turbulence like you see behind the airfoil now, but we will be figuring out how to make steady state flow solutions. And we're going to start with easy problems, and conformal mapping basically lets you solve, if I go back a little bit, something like this, or that, more that. Okay, so this is ultimate goal. Okay. So it turns out that in the same way that the stream function, or in the same way that gravitational field lines or electric field lines are perpendicular to their equipotentials, this is also true. So it turns out that lines of constant psi, streamlines, and equipotentials are perpendicular. Okay. So what on earth does this have to do with complex analysis? This treatment's going to be true for all of the three cases of potentials we talked about. So think about whichever one you feel most comfortable with. But this is the basis of conformal mapping, is we are going to define a complex potential. And it's going to be given by whichever way you want to do it. Turns out it doesn't matter. Potential plus I streamline. And again, you can think about this as electric potential plus I electric field lines, if you could figure out a way of defining the electric stream function, which is exactly what electric field lines are, or gravitational field lines. But because fluid flow is the most interesting application, I'm just going to say streamlines. And then I'm going to claim that all of the following are true. Each of these component functions, so remember that these are functions, so you can start thinking about them as functions of a complex variable. And you can start thinking about their output is u plus iv. And we'll complete that mapping in a second. So I haven't described what z actually is. So remember, we're 2D. So this is true if in 2D, so basically we take our traditional XY plane and we just map it onto the complex plane by just declaring the y-axis to be the imaginary axis. And then as we do that, we also take our field lines and our equipotentials and we upgrade them to being a complex valued function. So why would I do that? Well, it turns out I do that because once I upgrade this complex potential of a complex variable, then all of a sudden I get all of these really cool theorems about how well-behaved complex analytic functions are. So that's really the proof. So the fact that these two things are harmonic conjugates is really just a question of whether or not f is an analytic function. So if our potential field or our potential function is analytic, then what we get is both of the components of the complex potential are harmonic. And we'll prove that partly to jog everybody's memory about what this means. So this is the Laplacian, and the Laplacian is the divergence of the gradient. And we know what this is by definition. Because this is v, the velocity field. And aha, this was our first condition on the fluid, is that it was incompressible. So this equals 0 because we're incompressible. Or I'll just say for an ideal fluid. Okay. And then what I can do for the remainder is I can, so I actually should point out something first, is that this is Laplace's equation. So you can immediately see why we care about this is the relationship in between complex analysis and a whole class of physics problems, is that we've been solving the Laplacian a lot, and just any other method to do that, namely just say like, hey, look, these are analytic functions, let's upgrade them to being complex, and all of a sudden we have all of this machinery of complex analysis, is really useful. Okay. And then for the remainder of this, I can just say gradient of the real and the imaginary parts is equal to 0. So I'm using subscript x and y as derivatives with respect to. So just writing out these two pieces. So this is the stream function partial derivative with respect to x, and stream function partial derivative with respect to y. Okay, so that's what that means. And I know two things about this. I know that they're locally perpendicular, so I know this is equal to 0. But then I also know that if I were to take this and work out the components, what that's really saying is this must be true. Up to a constant. And what are these? These are the Cauchy-Riemann conditions. Okay. So our initial definition, in a sense, our geometric definition of the relationship in between the equipotentials and the streamlines translates, once we upgrade these to complex functions, into these two things being harmonic conjugates, is really what we're saying. So these are harmonic conjugates. So perpendicular is essentially the Cauchy-Riemann conditions. Okay, so cool. So what? The so what is what we'll get to in class, which is essentially the realization that if I take a harmonic function, so let me just clear this and do this really quickly. So let's say I've got some complex valued thing and it's analytic. And let me just take a function of my function. And W is also analytic. It turns out that what this is going to do is this is going to change the field lines. Obviously, I'm applying some function to it, but it's going to preserve angles. So this is what's called a conformal mapping. And by preserving angles, essentially what that means is we preserve the relationship in between the streamlines and the potential. And that means that it takes us from one correct physics solution of the Laplacian to another. So think about this in the following way: is you worked really, really, really hard for like your first 3 solutions for a potential. And then now what I'm telling you is any analytic complex function that you can think of will get you a new one. So you've actually gone from 3 or 4 solutions of the Laplacian, for spheres and for large plates and wires, to an infinite number just like that. And so we'll talk about specifically how that works and show some mathematical examples in class.